Okay, ELE 111, this is Chapter 7, Section 1. This is the starting point for your series parallel experience. Everything that we cover in here is actually applicable to circuits with capacitors and circuits with inductors. As you recall, we did series and we did parallel with RC and RL. And by the time we're done with this module, we will have done RLC circuits, which are series parallel. That means there will be capacitors and resistors and inductors piled together to form series parallel combinations. What we will not do is get into the sections on combining all three parts. We'll save that for the next class, ELE 112. And that will lighten the load for us on what we do here. So let's dig in. If you take a look at the top of this slide, it says that a series parallel circuit consists of combinations of both series and parallel current paths. It's important to be able to identify how the components in a circuit are arranged in terms of their relationship. If you think a series circuit is parallel or vice versa, everything falls apart. So to be able to do a series parallel circuit, you have to understand what a series and what a parallel link are, and you have to be right 100% of the time. There's no way around it. If you're wrong, you're going to have a very tough time. So let's take a look at a picture here down below of a bunch of resistors. ... Okay, R1, R2, R3. What you can say about these three resistors is that they are end to end to end. That's A, that's B, that's B, that's point C, and that's point D. And what you can say is that this thing is formed like a snake. One piece connected to another piece, connected to another piece. There's no branching off. The current can't escape. Whatever current enters A leaves at D. Do you see that? End to end to end. We're looking for things like that. These three circuits up here don't have that. These three examples are completely different. We will get into those circuits in a little bit. They are series parallel circuits. They're just small series parallel circuits. And there just happens to be no more than one resistor in any series path. So if you understand that series circuits are like a snake, where they just go from point to point to point without going anywhere else, you can see that whatever current comes through here stays inside that piece of wire and goes through all the resistors all the way through to point D. Okay? Now, parallel is different. A parallel circuit looks like this. You see, and they're connected at what are called junctions. And you might have resistor 1, resistor 2, and resistor 3 here. And these components are hooked what I call back to back to back. There's only 2 points of contact, and every circuit component is touching each other. So what I mean by that is there are 3 point A's, and all the resistors are hooked to that spot, and there are 3 point B's, back to back to back. That's what you call a parallel circuit. here is an example in the black circle up top. Here is another example because it's the same circuit, so it's the same example. Now, what is not a parallel circuit is that resistor that sits up there up top. Okay? So, now that you've seen what piggyback and back to back to back looks like, you have to be able to play like a detective and be able to find these situations throughout the circuits that you examine and work in this class. Okay? What else do we want to say? If we go to the next slide, which happens to be the same slide, and we blow, well, we can't do that. So let's take a look at these circuits. Here's a typical simple series parallel circuit. It don't get much simpler than this. You've got point A and B, and you've got a parallel branch, and the current flows, as you can see here, this is parallel, and this is in series with the parallel. So all the current flows into R1, but then it splits through R2 and R3. Whatever was up here is the total current of the circuit, and whatever's down here is split. But when it goes back to the battery, we're back to IT. So, if you will, whatever current goes in comes back to the battery. This is true of any circuit on the planet. This was true when we had series circuits. If you think of a series circuit as one that looks like this, here it is. Here's the battery. Whatever current leaves comes back. If 1 amp leaves, 1 amp comes back. Okay, that's what happens in a series circuit. Now, if part of the circuit is parallel, like what I've drawn now, the circuit has gotten more complicated. And whatever I draw in now, there we go. Now we have a monster series parallel circuit. The crap that's going on over here is very complex, but the bottom line is whatever current leaves the battery comes back to the battery. So there's an IT at the output, and there's an IT at the input. Okay? And we've been looking at this circuit now 3 times, and I just want to reiterate that we have a parallel branch sitting over here. If we say that this was 100 ohms and this was 100 ohms, then we could say that the parallel branch, due to product over sum rule, or the 1 over, would produce 50 ohms. Okay, try that. 100 times 100 over 100 plus 100. This is the product over sum rule, right? Don't lose it now. R1 plus R2. Remember that formula? Don't lose it now. Okay, you're going to need this formula in this chapter. If you were to produce 50 ohms out of the parallel branch, then this value up here, let's say that this was 100 ohms, then you would have 150 ohms of total resistance in this circuit. And what we would do is we would break this circuit down if we were working a problem and we had, say, 50, well, let's call it 100 ohms here and 50 here and 50 here. What we would do is we would take the original circuit, then we would break it down by adding the R total of the parallel. Let's see if we can do that. Parallel. We would take this and do R2 in parallel with R3 to produce the parallel value. We would still have 100 ohms on R1, and then we would draw another picture, and we would have RT, which is R1 plus this value here that we calculated. That would be the RT of the whole circuit. In other words, we would put an ohm meter in here, and the ohm meter would measure 150 ohms due to all the resistance in the circuit. The meter is inserted in exactly the same spot as the battery. So to measure resistance, you have to turn voltage off, you have to remove the battery, and you have to insert the ohm meter. Okay, here is another look at a series parallel setup, and you've got to play detective. You've got to be able to come in here and say, oh my goodness, there is a series circuit sitting in here, and there is another series circuit sitting in here all by itself. But you see, those two pieces of series circuits are not connected to each other exclusively because of this resistor in red is in the way. So what we're going to learn is we can visually inspect and see these two series circuits, but we have to handle resistance from the outside looking back, meaning we have to take R3 over here and combine it in parallel, because this is parallel right here. We have to add those two together. Let's say they were 100 ohms each. We would have 200 ohms here in the red circle in parallel with, say, 100 ohms over here, and we would have to deal with that before we go back and add these two resistors here together and combine them. And, you know, as we move through this material, it will become clearer and clearer. This is just a quick part one introduction to things.